Welcome back. Now on to practice. On the back you have a few examples where you're going to apply your knowledge yet again. mgx is equal to force of friction static because it's resting, the box is resting on the board. Then I'm going to say it's going to be 12 times 9.8 times sine of 7 degrees. Remember that. And that are congruent angles, whatever that is. And then 12 times 9.8 times cosine of 7 will be this. So this is force of friction, static, and this will be force normal. Normal force is equal to mgy. If I mark that as mgx and mgy, that is also helpful. Just don't draw actual forces there because they don't exist. Those are just helpful for us to kind of eyeball and remind ourselves the relationship between the two forces, friction and mgx and normal and mgy. If the coefficients of friction between Amazon box and the ramp are static and kinetic, what is the maximum angle? So the shortcut is very simple. Remember at the end of the last video or at the end of the lab, we discovered that the tangent of the absolutely maximum angle at which the object still stays at rest actually equals mu static. So then the angle is going to be the inverse tangent of mu static. Boom. So you just need to say that your theta is the inverse tan of 0.44. There you go. Then it will be less than 60. So when in number 3 I'm saying what's going to happen if it's at 60, because tangent of 60 is way bigger than mu static, then it slides. Now if it slides, then we have a slightly different picture here, or I should say free body diagram, not just a picture. It's a special one. I'm going to make friction slightly shorter than mgx. That will indicate that the box is actually, and it can be kinetic, is actually sliding down. Net force, which is mass times acceleration. Vertically, we don't have a net force, so I can say net force y is 0 because Fn equals mgy. So if I subtract one from the other, we're going to have a fat big 0. So there is no net force vertically. However, horizontally along the incline, there is net force. We can say net force x. So net force x is going to be mgx minus force of friction. So mgx again minus mg cosine of 60 degrees, and then squeeze the little mu before that. Because what is force of friction? Remember, force of friction is mu times normal force. Now the important part is which mu are we going to use this if the box is sliding? Mu k. Very important. Do not use mu s. So once you find that net force, I can even factor out mg to save myself some time on the calculator. It's going to be sine of 60 minus mu cosine of 60. If this is daunting, you don't have to do that. You can just step by step find your mgy, find your mgx, find force of friction, subtract friction from mgx, get that number, divide by mass, which is 12 kilograms, and voila, you will have your acceleration. Now, the extra challenge, the idea behind this one, what is this maximum and minimum pull that you can apply to keep the object resting on an incline? Working with the same example. In this example, we know that they yanked the ramp so high that force of friction static is not enough to counteract force of gravity, specifically its x component. So mgx here is greater than force of friction static. Then your minimum force of pull that you can add to that force of pull plus force of friction static can be equal to mgx. That will be the minimum force. And then if you pull too hard, what friction static is going to do, it's going to flip on you and it's going to get you the backward lash, and then you pull. I'm intentionally drawing it as long as it was before. In that case, this is your max pull, and that will be equal to force of friction static plus mgx. That's how you solve this extra credit problem. I'll see you in class. Thank you for watching.